Section 8.5. So we're going to try to tie the quantum mechanical model into the periodic table and these ideas of electron configurations. So the chemical properties of elements are periodic because the number of valence electrons is periodic. Okay, we saw yesterday that elements in the same column in the periodic table have the same number of valence electrons. It's because they have the same number of valence electrons that they have similar properties. And the orbitals that those electrons are occupying are the same types of orbitals as the other elements in that column. So let's look at a couple of these columns. The noble gases. If we look at the electron configuration, this is just the valence shell for these elements. We see that they all have a full valence shell. Now, helium is the baby brother of this family, or actually probably the baby sister because these are nonmetals. Helium is only 1s2, but that is a full shell. The first principal energy level can only hold 2 electrons. So even though helium does not have 8 valence electrons, that valence shell is full. Having a full valence shell is a particularly stable place. In my goofy chemistry world analogies, these are like the cool kids back in high school, the ones that just seem to have it all together. They're rich, their parents give them brand new cars for their 16th birthday, they wear all the right clothes, they go to the right parties, and everybody on some level wants to be like them, right? Some people are just willing to do more to be like them than others. But this 8 electrons, neon, argon, krypton, xenon, radon, they all have 8 valence electrons. That's like the hallmark of being cool for the elements. Okay, in a little fancier scientific talk, that's just a lower energy state. It's particularly stable. And so the elements are going to behave in a way that will get them to having that those 8 valence electrons. So these noble gases are particularly non-reactive. Helium and neon are basically inert. They really don't undergo any reactions at all. And for a long time it was believed that none of the noble gases formed any compounds at all. We now know that they do form a few compounds, but they're very unreactive. They do not burn, they're just very unreactive. And noble gases, it's like the European nobles, they just don't interact with the common people, the rest of the elements. Yeah, I kind of said all that. The alkali metals at the other end of the periodic table, and by the way, the periodic table, we see it as flat, but just like a map of the world is representing something that's spherical, right? Really, the periodic table of the elements should be a cylinder. And you should take the 2 ends and bring them together, and it should just go around in a spiral. And so really, helium and lithium are next to each other. Helium has 2 electrons, 2 protons. Lithium has 3. So right next to, around this break in the periodic table, we have the alkali metals. And the alkali metals are very reactive. And we look at their electron configurations. They all have 1 electron in their valence shell. 1 electron. This is not a particularly stable situation. Because if sodium were to ditch that 1 electron, if he were to take off that dorky sweater his mother made him wear, his t-shirt underneath is pretty cool. And so then he's going to look like neon. Sodium has 11 electrons, neon has 10 electrons. I see the electrons, they're on the outside of the atom. That's more like your hairstyle, your makeup, your clothes. It's what's on the outside. You can't change what's on the inside. You can't change who you are, no matter how much you try. You're still you. And these elements, the atoms, do not change their identity. They don't change the number of protons. That's what makes them a part of an element. But they can change the number of electrons. And so we see that sodium and all of these elements, in fact, will very readily lose that 1 valence electron. When they lose that electron, now they have the same electron configuration as a noble gas. They do not become the noble gas, but they have the same electron configuration, which is particularly stable. And so they do that quite readily. So they lose that ns1 electron here. N is the principal quantum number. N is just the period 1, 2, 3, 4, 5, 6, etc. And in doing so, they form +1 ions. So they are very reactive because it's easy to just lose one electron and become especially stable. The halogens are on the other side of the noble gases in the periodic table. They have one fewer electron than the noble gases do, and we see that they all end in S2P5. Well, I think of all these elements trying to be like a noble gas in terms of their electron configurations. So fluorine has two choices. It could gain one electron, or it could lose 7. Which one's going to be easier? It's going to be easier to gain one electron. If fluorine gains one electron, it has the electron configuration 2s2, 2p6, which is the same as neon. On the outside now, it looks like neon. I'm personifying atoms, okay? I fully admit that. Why would it do that scientifically? Because it's more stable. It's a lower energy state to have those full valence shells. So the halogens tend to gain one electron, and by doing so, they attain the electron configuration of the next noble gas. The halogens form anions with a -1 charge. Now, we learned this part before when we talked about nomenclature and ionic compounds. We learned a little pattern on the periodic table of how we could predict what ions these things form. But quantum mechanics explains why they do that. You see? So, learning what is good, but learning why helps us to understand even more. So many of the nonmetals and the metals form an ion with only a single ion. And we learned how to predict that from the periodic table. Group 1A is 1 plus, group 2A is 2 plus, group 7A is 1 minus, group 6A is 2 minus, etc. The reason behind that is because when they form those ions, they have the same electron configuration as the nearest noble gas. So all of these guys form -1. Because by gaining an electron, for electron configuration purposes, they essentially move over 1. Everybody's trying to get over to here. This is where we're getting. And so these guys need to gain 2 electrons to get over there. Nitrogen needs to gain 3. I'm not sure why they always leave phosphorus out of this. I'm going to put him in because I think he feels a little left out. Phosphorus also forms a -3 ion. Now, what about these guys in group 4? The one on the top there's carbon, and then there's silicon. What does carbon do? Have we dealt with carbon ions? Well, it's like halfway between, right? It could gain 4 or it could lose 4. Neither choice is really easy to get to. And so carbon, for the most part, doesn't form ions. And silicon and germanium, which are semi-metals, they don't form ions too much either. And so there's kind of a reason that those guys are not in our list of elements that form predictable ions. Here's carbon has its own set of rules for names. Because of carbon's position there, it's got 4 valence electrons, and we'll learn that it tends to form covalent bonds. Instead of transferring electrons, either gaining or losing, it will share electrons. And because of that, it does a lot of cool things that other elements don't. And you can make these long chains of carbon atoms in these compounds, and we just barely touched on naming organic compounds. But yeah, the fact that carbon really doesn't form ions has a lot to do with it behaving differently from the other elements. Here we've got aluminum. Aluminum is 2s2, 2p1. To get a noble gas configuration, it could lose 3 or gain 5. They're going to take the easy way. So aluminum's going to lose 3 and become a 3+ ion. And we talked about these guys already. In the group 2, they're going to lose 2 electrons. Magnesium losing 2 electrons goes over here and has the same electron configuration as neon. In fact, let's just look at that real quick. So let's look at calcium. Using noble gas shorthand, what's the electron configuration for calcium? Argon. 3s2, right? Sorry, 4s2. Thank you.
The numbers on the side there.
Nice. Good grief. He found another typo. They numbered these wrong because they left hydrogen out. Okay, well, I can fix that, and I will, because things like that bug me. Man, I wish I could do this in real life. Of course, then I'd spend hours erasing the dirt on my house. So 1 is up here. This is 2, 3, 4, 5, 6. That's better. Thank you. So calcium is here. These guys aren't shown here, but this is neon, and this is argon. So to write the electron configuration for calcium, we look at the next row up, argon. It's going to have the same electron configuration as argon plus 2 electrons here. This is the S block, and this is the 4th period, not the 3rd period, and so 4s2. So, looking at the electron configuration this way, we can see that if calcium loses those 2 electrons, it's got the same electron configuration as argon. But the number of protons doesn't change. It still has 20 protons. It used to have 20 electrons, now it has 18 electrons, and so now it has a 2+ charge. And that is why all the ions listed on this table form the ions that they do, is to get the electron configuration of a noble gas. Any questions?
Yeah, so in group 1, those have the tendency to be most reactive. And such that first bond, the covalent bond there, or an electron, it has the most energy. So is that why they're so reactive? Is 1+?
Yes, these are the reactivity and the driving force for the alkali metals to lose an electron has to do with the difference between the energy level as the atom and the energy level as the ion. The energy level as the ion is going to be lower because of the stable electron configuration. For these guys to achieve that, they have to lose 1 electron. The first electron requires energy to pull it off. I mean, this is part of the atom. They don't go around just giving them away. Oh, I've got this extra electron. Do you want one? Here. Just giving them out, right? It's part of them. You have to pull it off. It requires energy. But the first one is easier to pull off. The second one is harder, and the third one is harder. So the more electrons you pull off, the harder it gets to pull those electrons off. It requires more energy. So these guys, by losing 1 electron, they have a smaller outlay of energy for the gain of being lower in energy. Magnesium, calcium, strontium, barium, they have to lose 2 electrons. So they have to lose the first one, and then the second one, which is even more, so they have more outlay of energy. They have more energy has to be expended to make them into that ion to get to that stable state. Does that make sense?
Yeah.
Kind of.
That almost, but it makes it sound like they could be more reactive yet. As you go left, they become more reactive, right? With the anion.
Well, you have to, you think about making an investment. So the group 1A metals, you make a small investment, you get a payoff. Here you have to make a larger investment to get the payoff. Well, it's harder to convince people to make the big investment. It's easier to convince them to make a small investment. And you go over here to aluminum, and it's an even larger investment for a payoff. Does that help? Not really?
Yeah, maybe I'm not conveying what my thoughts are, so it's okay. I can talk later about it.
Okay. Does anybody else have any? Yes?
Why is it so much more important to have their electron configuration at lower energy level than to be electrically equal with the positive and negative charges of that metal?
Well, that's a good question. Why is it more important for them to have this more stable electron configuration rather than to have their charge be neutral as an atom? Well, in order for any of these atoms to become ions, okay, these guys are losing an electron. They don't just lose an electron and become an ion, which reminds me of a joke. 2 sodium atoms are walking down the street, and one runs into a lamppost. He's like, ah! And his companion turns to him and says, "Are you okay?" He's like, "Yeah, I'm okay. Are you sure?" "Yeah, I'm positive." Because when he ran into the lamppost, he knocked an electron off. I didn't tell that one very well. It works so much better in my head. When an atom loses an electron, it has to go to something. So let's look at sodium. If sodium's going to become an ion, it has to do so in conjunction with somebody like chlorine becoming an anion. When the sodium atom loses an electron, the chlorine atom gains an electron, then they are attracted to each other, and there's something called a lattice energy when sodium chloride forms. And that is the real driving force behind all of this happening, is now we've got these opposite charges attracting to each other, and they form little salt crystals. And so, it's good to think about the energy and the driving forces behind this, but unless we're going to get really deep into it, we have to stay really on the surface. There's no kind of middle ground talking about this. But it all comes down to energy. All comes down to energy. And so there's energy required to remove an electron. But when a compound forms, whether it's ionic or covalent, there is an energy involved with that as well. And so whether stuff happens or not depends on whether the energy is coming in or going out. Does that help? Yeah, because why would nature separate charges? Well, it separates charges, but then it puts them back together in a different way. Yeah. Any other questions? So we need to be able to do electron configurations for ions. And if you can do them for atoms, doing them for ions is just a baby step past that. So anions get formed when a nonmetal gains enough electrons to have 8 valence electrons. So in those situations, the s and p orbitals of the valence shell are going to be full. If we look at sulfur, a sulfur atom has this electron configuration. The first shell is full, the second level is full, and the third level has 6 electrons, which we could predict by looking at the periodic table. Sulfur's in group 6A. To have 8 valence electrons, it needs to gain 2 more. And those 2 will go into this unfull p orbital, p subshell. So then we end up with 3p6. Now this is the S2 minus anion. The number of protons has stayed the same, but it's gained 2 electrons. And this is the same electron configuration as argon. So they're all going to go to an electron configuration that is the same as the nearest noble gas. Cations do a similar thing, but they're losing valence electrons. They're going to lose all their valence electrons. And that results in a new lower energy level. But this process is always endothermic. You have to put energy in by pulling these electrons off. This is not something that just happens spontaneously. Electrons don't just fall off of metals. Sometimes we talk about it that way, but that's not what happens. So here's magnesium. It has this electron configuration. Its valence shell is 3s2. It's got 2 electrons in here. When it forms a cation, it's going to lose all of those. We don't see magnesium +1 ions. We don't. It's either going to keep its electrons or it's going to lose both of the valence electrons. And so this one, this section here, just gets chopped off. Now we have magnesium 2+. This is a cation. And now, what's underneath? Here the valence level was 3. If we peel that off, you can kind of think of this as like layers of an onion, and the outer layer wasn't complete. So we peel off that partial layer on the outside of the onion, and what's underneath? A full valence shell. Because the electrons in all atoms fill the same types of orbitals in the same order. So their electron structure is very similar. The energies of those orbitals are going to be different, but the basic idea of filling the 1s and then the 2s and the 2p, all of that is the same for all of the atoms. So then this ends up with the same electron configuration as neon. So any question about electron configurations? Because we're kind of leaving that now. You need to be able to write electron configurations. Yes?
So, can you, like,
do another one?
Further down? Yeah. 'Cause
Sure.
I think it's confusing.
Yeah, we can do another one. So let's look at, how about cesium? So let's look at cesium. We'll just stick him in here. Should we write the noble gas shorthand or the whole business? Noble gas? Okay. So we look at cesium on the periodic table. It's in period 6. So we go up to period 5 and we go over to the end and we see the noble gas there is xenon. So the electron configuration for cesium is xenon plus 1 electron, and that's in the 6s1. So when cesium becomes a cation, it's going to lose the valence electrons. And so losing that 1 electron, it now has a +1 charge, and its electron configuration will be the same as xenon. Does that help?
Will it really be the same? Like, is there any way of specifying that it's cesium?
Well, when we write an electron configuration, there's usually some indication of what ion or atom we're writing it for. Because if I just give an electron configuration, I hope the book goes into this, I hope the slides go into this. So if I write this, 1s2, 2s2, 2p6. What is that an electron configuration for? For an atom, that's neon. What anions is that an electron configuration for? Nitrogen, oxygen, and fluorine. So N3 minus, O2 minus, and F minus. all have that same electron configuration? Are there any cations that have that electron configuration? Yeah, sodium, magnesium, and aluminum. It's a very popular electron configuration. All of those ions and the element neon have the same electron configuration.
So this is only for the predictable.
We're talking about the predictable ions now. We're completely ignoring the transition metals.
But if it did happen to the transition metals, it would still happen to an outer shell, right? So it was like
What's tricky about the transition metals is they have those d electrons that are not so predictable. And so if we look at something like iron, here, I'll bring up a new screen. Let's look at iron. I'll just write up here. So iron. Electron configuration for iron is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 1, 2, 3, 4, 5, 6, 3d6. That's an iron atom. How many valence electrons does iron have? 2. These guys. So very good too. So what would we expect to happen? We expect it to lose its valence electrons and form an Fe2 plus ion. Does it do that? Yes, but it also forms an Fe3 plus. Why would it do that? Well, remember we talked about half-filled things having particular stability? So it's lost those to become this guy. Now we've got this 3d6 and we have an empty 4s. What if we took one of these and we had 4s1, 3d5?
wouldn't it do that first?
Well, it might or it might not. But if it did that, so we have Fe2 plus, and then it does this. It takes this 3d6 and says, oh, but there's this deal on at the hotel. And if I have 2 rooms that are exactly half full, I get a discount. So hey, let's go for that. You move over here, and then we all get our own beds, and it'll be great. Well, look, here's a valence electron. If it lost that, it becomes Fe3 plus. Now it's got an empty level and a half-full 3D shell, subshell. Okay, so we are not going into the details of how all the transition elements do what they do, but that's one example that's relatively easy to understand. Okay, when we've got the d orbitals involved, things can get messy and unpredictable. When you look at it deeply enough, it is reasonable. There's explanation in terms of energies and calculations that you can do, and you can see, oh yes, I see why it does that. Now, would you necessarily be able to just predict that by looking at it? Absolutely not. But that's a very good question. Any other questions?
So on a test,
Pardon me?
The S, SP, SP, SD. How do you memorize it? Is there a pattern?
How do you memorize the order? There's a pattern in the periodic table.
Okay.
Okay? So let's go back to that. So here's the pattern in the periodic table. So here's, we'll just, we're going across. Here's 1s1, 1s2, 2s1, 2s2, 2p3, 2p4, 2p6, 2p1, 2p2, blah, 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 to 2p6. Here's 3s1 and 2. Here's 3p filling 1 through 6. We come over here, 4s. Up to there, it should be pretty clear. Okay, so now we get to D, and you might think, well, that should be 4D, right? But we skipped the 3D. And so this is where I think it fell. It sunk. Like the valley, I just read an article this morning. The valley is sinking because we're in a drought and we're pumping so much groundwater that the ground is actually sinking a little bit. So that's what happened here. Because wouldn't that be, well, let's see, like this? Wouldn't that be more predictable? You know, just one. Why is there a leap of 2 there? And then there's this leap of 2 over here. So I envision this as it was supposed to be up there, but it sunk down. So this is 3D, and this is 4D, and 5D, and 6D. So we do the 4s2, then we fill the 3D up to 10, and then we've got 4p, and 5s, and 4d, and 5p, and 6s, and 5d, and then this is where these guys come in, and they sunk 2 levels. So this one looks like it should be 5f. No, it looks like it should be 6f, right? Because it's coming in here on this period 6. But it's actually 4. So this is 4f and this is 5f. So we've got our main groups, which are these sections that stick up. And the quantum number, principal quantum number, is the same as the group number when they're written correctly. 1, 2, 3, 4, 5. So this is 6s and this is 5p, right? The D sublevels are sunk down. So you take the period number and you subtract 1. The F are sunk down 2. So you take the period, and you're like, well, what period is this supposed to be in? Well, it came from in here. Actually, maybe I drew the line in the wrong place. Yeah, I did. I drew the line over 1. The line's here, actually. And how can you figure that out? Like the periodic table on the back doesn't have the line. Well, look at the numbers. Cesium's 55, barium's 56, lanthanum's 57, hafnium's 72. What happened? Oh, they're down below. Okay, so that's, I think that's the best way to do the pattern. That help?
Yes.
It's all right there. And you will always have a periodic table. You just cannot do chemistry without a periodic table. I have 2 periodic tables on my cell phone. It's just a security blanket. I need to know what the molar mass of barium is, right? Just need to be able to find that out. Yes?
When do you start pulling up the F block, like 4F1? Do you get to that after you do 5D1 or before?
Well, the simple answer is that you would just go in order. So looking at the periodic table in the back that has the actual numbers, this would be, oops, wrong place. This is 6s1, 6s2, 5d1, and the next element is actually this guy down here. So that would be 4f, 1 through 14. And then you would come back here and 5d2. 5ds and then the 6p's. So I think that is the basic idea is you just follow the order through. Now, as we saw with those irregular electron configurations, there are some exceptions to those. And we're just not even going to deal with the F block elements very much at all. You need to know that they're there. And if you do like an electron configuration for, let's see, I think lead is right here. His electron configuration is going to include a full F block, right? So you need to be aware of those, but I don't know that we have ever used these elements for writing electron configurations. I mean, we run into some things like gold and platinum and mercury and lead that are down there in the bottom of the periodic table, but the lanthanides and the actinides, those are crazy things. About the only time we deal with those in general chemistry is when we're talking about nuclear chemistry, because a lot of them are radioactive. Yes?
This periodic table in our notebook looks a little bit different from that.
Mm-hmm.
So would lanthanum 57, would that be a 5D1, or is that part of it?
Well, it,
Because in this one, it kicks it down to these
it would be a 5D1, because otherwise the numbers don't work out.
And so if you're doing like mercury, would you put all of 14 and just list that D1 as part of the full D?
For mercury would end with 5D10, and before that would be 4F14.
But would you list the
You would not list the 5D, I would not list the 5D1 before the 4F14.
only if you're probably doing one of these?
Only if you're just stopping in one of the lanthanides, yeah. And that gets into all these like kind of crazy things, and that's not my goal in teaching you, is to have you worry about these crazy things at the bottom. Because if you need to go on in chemistry, and you go into a branch of chemistry where they care about crazy electron configurations of lanthanides and actinides, they'll teach you. But they're going to assume that you can competently write the electron configuration for strontium. And so those are weird things that just, we just don't need to think about too much. Any other questions?